Hello everyone, welcome to Physics Mage. Dear students, here today we have a network in which we have capacitors as well as some cells. We need to find out the charge flown through the switch from A to B when it is closed. This is kind of an interesting problem, so we'll see how to solve this. So since we need to find out the charge flown from A to B when it is closed, so dear students, we have the network where we can easily recognize the batteries like plus minus. Here there is one more battery, 10 volts, and here plus minus 5 volts battery, and rest of them are capacitors. There are 4 cells and 3 plus 3, 6 capacitors, correct? So we'll try this by just first analyzing like the approach. So I hope you're all familiar with this KCL and KVL, but today here we will plan to solve this one by using nodal analysis. So here in this technique, I'm going to virtually ground one point such that that point will be at 0 voltage. Okay, this point is at 0 voltage. Since this is a conductor, even this point will be at 0 voltage, right? This is at 0 voltage. So you know that even this point will be at 0 volt, and if this is at 0 volt, this would be at a minus 5 volt because we need potential difference to be 5, right? And this side it should be higher potential when compared to this side, so it is minus 5 volt this side. Then we have here this other points. If this is at 0 voltage, this point would be at plus 10 volts, and that's it. Here we have a capacitor. We can't just say what is the potential at this point just like that. So even whatever the potential we have here, the same potential will be there here. So what I will do is I will introduce one variable saying that this will be at x potential. Then if this is at x potential, even this will be at x potential, and I will call this will be at y potential. If this at y potential, even this will be at y potential, even this y potential, this one at y electric potential, right? So we have marked all the nodes available in this circuit, and now we are good to go. We can solve this problem. Now the logic is we need to find the charge flown through this. So here our usual assumptions here, we always think that the so-called system where the capacitors, right, these are all uncharged. Okay, so all these capacitors we usually take all these 6 capacitors. They are all uncharged capacitors initially. Then we are going to place them in the circuit such that they will have some charge on them now, because now electrostatics is established, so it is charged condition. Now this circuit, right, if you want to know like how much charge flows from A to B, first I want you to redesign the circuit in a way which is convenient for us to handle. Okay, so as of now you can look at this. Let me highlight that by using green color. See, observe that since we need to find out the charge flowing from A to B, right? So I want you to think about this and this, this one, and this. So if you consider only this green part, you can see that it is like an isolated system. It is an isolated system before connecting. Meaning if I don't connect A and B, that green part is isolated. Isolated meaning we know that it cannot exchange charges with the other stuff, right? So the batteries are there, sure, but batteries can never create charges. It can only drive the charges. Batteries drive the charge, that cannot create the charge, as you guys already know. Okay, so we don't have to calculate like what is the initial charge present on it unless there is a question like that. So what you have to do is you can just observe the plates involved. So this is one plate, so let me highlight that with some color. So let me choose some like some yellow color. This is one plate which I'm interested in, and this is another plate, and this is one more plate. Okay, so we know that these three plates will be considered as isolated, let's say, so that it cannot exchange with the other stuff, okay, other parts of the network. Fine then. So then we'll randomly mark the charges. So I am just assuming this here. There is no like strict rules like this is how it should happen. So what I will do is I will first redesign the circuit so that we can have a better command on the circuit. Okay. So what I will consider is, let me take this is at X potential. Okay. This is at X potential, right? So from X potential, we have a capacitor which is 6 microfarad, and that is connected to a potential of plus 10 volts. Okay, so then X that has two branches. One is like this with a cell where plus minus we have 5 volts. Then we have a like 3 microfarad capacitor there, 3 microfarad capacitor, and that point is Y. And there is one more channel which can lead us to the same location of node. So that is 3 microfarad in the another branch. And from there, we are going to this point. Okay. So what we just used is, I have taken care of this arm and this arm. Okay. So, and I have joined these two nodes and joined these two nodes and forming a circuit like this. This point is X, that point is Y. Okay. Now you can see that for Y, if you connect these two branch arms, right, there is another two. So we'll take care of that also now. So we will consider this particular arm and say that it has one plus minus 10 volt cell followed by one 3 microfarad capacitor. Then we have a zero potential, 0 volt. Okay. Then one more branch we have, which is about this one. We have a 6 microfarad capacitor, 6 microfarad capacitor, followed by minus 5 volts. Okay. So this is what we have in our system. Okay. Now, A and B are not yet closed. So this is how it looks, right? So I just wanted to highlight this one, that our green color, this isolated part, right? That isolated part here is this one, 6 microfarad and 3 microfarad. So here 3 microfarad and this 3 microfarad. That is not in connection with any part of it. So no charge can enter into that particular green color like region and leave that. So charge should be conserved there, meaning initial charge, meaning before like connecting capacitor to the batteries, if they are chargeless, then after connecting to the batteries, even though charges will appear there, so that has to be conserved, meaning initial charge is zero, final charge will also be zero. So I'll be just marking some charge flow here. So let me guess like this. Okay, so since this is plus and X, so I'm just guessing that this might be Q1. If this is Q1, let me say this is Q2, that is Q3, and Q2, Q3 will go like that. Then this might be Q4, that may be Q5. I'm just guessing this, okay? Like randomly. Maybe I may be wrong, okay? So still, I will get the right answer as the proper magnitude values, and you guys know like how it works. If I get the charge, suppose let's say Q4 is negative, then you know that the marked arrow is wrong and the direction would be opposite. But still, I will get the right answer, meaning the magnitude value will be correct. Only thing is minus implies that the assumed direction is not proper. Okay, but it works. Now let me just keep the arrow like this only, meaning there is no strict rules like where we have to take. So we'll keep it like that way. Okay, now we have Q1 like this, Q2, Q3, Q4, Q5. We have marked that. Now the question is, sir, like should I solve this? Like see, if if they ask you like what is the change in the charge on any of these plates. Suppose if they ask what is the charge on this plate, meaning I'm highlighting this, right? That plate, what is the charge initially? After connecting A and B, what is the charge finally? Find out the delta Q, change in the charge or something. Then you have to solve this like for the initial condition. But anyways, they are not asking, right? And we know that this is isolated. Since it is isolated system, we know that the initial charge in the isolated system, that is going to be 0. Okay, so please make a note of that plates which we are considering. So this plate and this plate and one more plate is this. Okay, according to our marking, you know that we are looking for this one which is minus q1, and this one is going to be plus q2, and this one is going to be plus q3. So we know that q net initial is going to be minus q1 plus q2 and plus q3. If you solve this, you will get for sure 0. If not, your calculations might have gone wrong. Okay, so because this has to be correct, because initially this will be 0 before we connect them to cells. Okay, so this is something which you you might need to solve if they ask you to find out the changes happening on the chart, like changes happening in the charge on any of these plates. Okay, but since they are asking you to address what happens once you connect it, right? So for that we don't need this kind of circuit. What we'll do is we will redesign the circuit again in a different way. So observe, after connection of A and B. Suppose if I connect from A and B, we know that previously this was at X potential, this was at 0 potential. After we closing, the charges will flow from higher potential to lower potential until they both become 0, 0, meaning both become like same potential, right? So let us just close this and still we'll ground this, okay? So we know that this is at 0 potential, this is 0, this will be at 0, this is minus plus, right? So this is going to be at 10 volts, and definitely this would be at 0 potential. Then we have plus minus, and here plus minus, plus minus. This would be at minus 5 volts. Okay, so only thing which we have no idea is the potential here. So let me call that potential as some x dash. Okay, so if that is x dash, everywhere here x dash only. Now we'll redesign the circuit so that it should become easy for us to like check the charges present on this so-called isolated part. Okay, so here isolated part I'm highlighting. So this plate of 6 microfarad and this plate of 3 microfarad and the another 3 microfarad, this one, right, before switching on, that was isolated. Now we are going to consider this. I have shown here, it was isolated before. Now after connection, if there is any changes happening in these charges, right, then that has to be because of the exchange happening through that A B only, because only through A B charge can enter the so-called isolated part or leave the isolated part, correct? So I hope you can observe that from this diagram. Then we will now redesign this one. Okay, so based depending on our convenience, we can redesign this. So this is plus 10 volts. I'm starting from this point. So we are going like this 6 microfarad, which one of the plate of interest is there here. Then this is at 0 potential, right? So see, 0 potential, I'm going to just make it 0 like that, more obvious. From there, then we have like two connections, like, or three connections, let's say three connections, like 1, 2, 3. Okay, so first connection is with 5 volts, like that, 5 volts. Then a 3 microfarad, 3 microfarad, and followed by x dash. That is a potential there. Then the other one is just 3 microfarad to that point, 3 microfarad to that point. Then the one more fellow is like 3 microfarad, 3 microfarad followed by 3 microfarad followed by minus plus 10 volts. I'm just redesigning the circuit here. That is connected to x dash. then X dash is connected to minus 5 as well. So meaning from here, we have a connection to one more capacitor, which is 6 microfarad, that is connected to minus 5 volts, which is what we have here. Okay, now I hope you got this circuit. So now this point is anyways at 0 volts, and this point also we know. Only thing which we don't know is this X dash value, and now we can easily get that. So let me just highlight this idea as say some charge may be going like that, like Q1, this is Q2, that is Q3, this is Q4. Maybe I might be wrong. So I'm just randomly marking the arrows. If I am getting negative answer for this arrow, like negative answer for this charges, then my direction, supposed assumed direction, right? That is not correct. So it will be in the opposite direction, but still the answer is correct. Okay. So we know from KCL, we have this Q1 plus Q2 plus Q3 is going to be Q4, like at node whose potential whose potential is at X dash. Okay, that is what we just observed. Now we need to find the value of Q1, Q2, Q3, Q4. For that, I'm using KVL logic. Okay, using KVL, what I will do is get the values of Q1, Q2, Q3, Q4. Okay, so let us analyze the circuit by just observing this. Say I'll start from this point and proceed through this branch and observe that I was initially at 0 volts. Then I'll move from like plus to minus 5 volts cell and plus to minus, so minus Q1 by 3 microfarad. That is the voltage drop happening. After that, whatever the potential we have, that we are naming it as X dash, which means Q1 is going to be like minus 5 minus X dash times of 3 micro. That is your Q1 value. Now for Q1 we got it. Then we'll go like that for, let's say, Q2. For Q2 we have 0 potential initially. We are starting from this point. We are now moving in this line. So plus to minus minus Q2 by 3 microfarad. That is a voltage drop happening. That is equal to potential at X dash, right? So X dash, so we have Q2 is going to be minus of 3 micro X dash. Okay, so we're done with for Q2 also. So for Q3, we'll now see. For Q3 is this branch. We are starting from 0 potential, so plus to minus. So minus of charge flowing through that branch is Q3, and 3 microfarad is the capacitance. So that's a voltage drop, minus to plus 10 volts. We are crossing the cell, then which is equal to potential at the node, which is X dash. So we have Q3 is going to be like 10 minus X dash times of 3 micro. Then we have pending work for Q4. Q4 is going to be like X dash we are starting from. So plus to minus, minus of Q4 by 6 micro. That is equal to minus 5. So of course Q4 is going to be, Q4 is going to be like X dash plus 5 times of 6 micro. And of course, if you want, you can name this one as some charge like Q5 or something. So you know that Q5 is going to be equal to like the potential difference you have, like 10 minus 0, that divided by 6. Okay, so this is potential difference times the capacitance, right? So like 6 micro. So you'll have 60 micro coulomb is the charge flowing through this branch, like Q5. So you know that this is plus and minus. Okay, so this is what we have here. Now, what about like Q1, Q2, Q3, Q4? Do we have that values? For getting that values, we need to solve this equation, right? So let's say that is our equation 1, and all this one this one, even this one, and that is our equation 2. So we'll use equation 2 in equation 1, and we will try to simplify that. Okay, so as we plug all these values there, we'll have minus 5 minus x dash into 3 micro plus q2 is going to be minus of 3 micro x dash plus q3 is going to be 10 minus x dash times of 3 micro. That should be equal to q4, which is x dash plus 5 times of 6 micro. You just have to simplify here. You just see like what can be cancelled, like 3 micro, 3 micro, 3 micro. This is 2 times, right? So you can just simplify. This is what you'll get if you just cancel this 3 micro, and you'll have this multiplied. So 2x dash plus 10. This is what, like 3 terms, so minus 3x dash and minus 5 plus 10. So obviously this becomes 5x dash equals minus 5. So x dash is just minus 1 volt. That's what we have. Okay, so now we got to know that this point is at minus 1 volt. Now, if you know that, then you can just use that in equation 2's and get the values of q1, q2, q3, q4 and all. But our interest is what? Our interest, I'm going to highlight that using purple color. So these are the plates which we are interested, right? This 3 micro, 3 micro and 6 micro, which is connected across 10 volts and H dashes. Okay, so this is the plate which we are interested, and this plate and this plate. So please observe that, and once you can observe these are the places which are of our interest here, right? So then our interest is now to solve just q1, q2 and q5. We already have q5, so let's just solve q1 and q2, right? So q1 is this, so we can write q1 is equal to minus 5 minus 5 minus x dash is minus 1, right? So this into 3 micro, so that is going to be like minus 4 minus 12 micro coulomb, right? That is what we got for q1. So q2 is of our interest then. So q2 is minus 3 micro x dash, minus 3 micro x dash. So minus 3 micro x dash is minus 1, so it becomes 3 micro coulomb. Okay, so you have q1, q2. Then we already have q5. So q5 is like 60 micro coulomb, right? And as you know that if there are any charge exchanges happening to this isolated part, that is through A to B connection. Now we will find out like what is a charge here. So you know that 6 microfarad, this particular branch is carrying that Q5 charge. This is minus Q5 there, and this was carrying Q1 charge. It is plus minus, right? So we have Q1 there. This is Q2. So plus minus. So we will take now charges which is of your interest for isolated part. Okay, so isolated part you have q5 negative minus q5 should take, then uh, q1 plus q1 I'm taking, and plus q3, right? Plus q3, sorry, plus just q2, not q3. This is just q2. Q5 negative, so minus 60 microcoulomb that we have, then plus q1 meaning plus 12 microcoulomb we'll get. Then sorry, this is plus q1, right? Q1 is negative sign here, so you just have to write whatever the value of q1 there, and q2 is plus 3 microcoulomb. Because it was positive, I'm writing positive, right? So just same thing. So we have 72 plus 3, right? So it becomes minus of 69 microcoulomb. Okay, so this is the net isolated charge. Okay, so you know that if it is negative, meaning what? Here from this isolated part is becoming negative. So initially it was zero, right? Initially it was zero, some isolated part. this isolated part, initially it was having zero charge, okay, zero coulomb. Now if the charge leaves, it becomes negative, right? So it is becoming minus 69 microcoulomb, meaning then definitely the outgoing charge from A to B is going to be plus 69 microcoulomb. Okay, so I hope you understood this problem. When you close the switch, the charge will flow from A to B. So everybody, I think it's kind of interesting problem to try and solve. And here is the challenge. Suppose if you want to, improve your way of analyzing the problems. So try to find out what is the change in the charge, okay, happening on the split. So 6 microfarad we have, right? So find out the change in the charge. So delta Q change in the charge of this plate, and put that in the comment section. So we'll see how many of you can get the right answer. So thank you everyone for watching this, and I hope it helps you to prepare well.